Imagine a fuel so dense that a fingertip-sized pellet can power a home for years. That's uranium, ordinary-looking metal with extraordinary potential, but most of it can't do the job as is. In nature, only a tiny slice, uranium-235, splits easily to release heat, so nations run uranium through a precise, tightly guarded journey called enrichment, turning mined rock into reactor-ready fuel. Along the way, you'll see freezing mines, humming centrifuges, and robots packing ceramic pellets into silver tubes. You'll also see the guardrails, sensors, inspections, and thick concrete that keep the power under control. This story isn't just about physics, it's about how we make clean, steady electricity for millions of homes by carefully separating the right atoms from the rest. Uranium isn't one thing, it's a family of atoms called isotopes. The two that matter most are uranium-235 and uranium-238. They're chemically the same, but U-235 is slightly lighter and, crucially, it's fissile. When a slow neutron strikes a U-235 nucleus, it can split, fission, releasing heat and a few more neutrons. Those new neutrons can split more U-235 atoms, creating a controlled chain reaction, the heart of a power reactor. U-238, the heavyweight cousin, mostly ignores slow neutrons and doesn't split easily, so it contributes little to that chain reaction. Here's the catch. In natural uranium, only about 0.7% is U-235. The rest, about 99.3%, is U-238. Light water reactors work best when the U-235 share is raised to roughly 3 to 5%. That boost is what enrichment means. Think of it like a giant sorting job. Among a big jar of nearly all blue marbles, U-238, you're picking out the few red ones, U-235, and making a mix with more reds. Why can we separate them at all? Because U-235 is just a bit lighter than U-238. Precision machines exploit that tiny mass difference to tilt the mix toward U-235. Once we've enriched it, the fuel can efficiently sustain a steady, well-controlled chain reaction that produces heat and, ultimately, electricity. Uranium starts as rock, sometimes in massive open pits, sometimes in deep underground tunnels, and often today in well fields that look like a quiet grid on the prairie. In those well fields called in situ recovery, operators inject a mild mining solution underground, dissolve the uranium right where it sits, and pump the uranium-bearing liquid back to the surface. It's less disruptive on the land and avoids hauling huge volumes of rock. In other places, the geology is too unique or too rich for wells alone. Picture Canada's far north, where some deposits are so high-grade that engineers first freeze the water-soaked sandstone around the ore. They drill a ring of slim pipes and circulate sub-zero brine to lock the ground in ice, both stabilizing the rock and stopping groundwater from flooding the work. From safe, elevated bays, remotely operated drills cut pilot holes down to the ore. Larger tools then ream the openings, and robotic carts scoop the broken rock while powerful fans keep fresh air moving through the workings. Whether the uranium comes up as crushed rock or as solution, the next stop is milling, a chemical plant with the single job of separating uranium from everything else. Crushed ore is ground to a fine sand, mixed with water into a slurry, and treated in big steel tanks. Acids or alkaline solutions dissolve the uranium, but leave most other minerals behind. The uranium-rich liquid is purified in stages and then precipitated into a solid concentrate. The product is a mustard yellow powder nicknamed yellow cake, typically uranium oxide. It's dry, stable, and packed into sealed drums for transport. At this point, the uranium is concentrated but still natural. To make practical fuel, the yellow cake must be converted into a gas and sent through enrichment. Yellow cake is concentrated uranium, but it's still a rock-like powder. To separate its isotopes, we first need it as a gas. And for uranium, that gas is uranium hexafluoride, or UF6. Here's how the change happens. At a conversion plant, sealed systems receive drums of yellow cake and run them through purification steps to remove leftover minerals. The cleaned uranium oxide is then reacted with fluorine-bearing chemicals in corrosion-resistant equipment. The goal is to form UF6, a compound that behaves in a very handy way. At roughly room temperature, it's a solid, but warm it a bit, and it becomes a gas. That means it can be shipped safely in thick steel cylinders, then heated and fed as vapor into enrichment machines. Safety matters a lot at this stage. UF6 reacts with moisture in the air to create harsh byproducts, so the plant uses dry, filtered atmospheres, negative pressure rooms, and leak detectors. Workers monitor temperature and pressure constantly because UF6 expands as it warms, and the containers must stay within tight limits. Once a cylinder arrives at an enrichment site, it's connected to a closed manifold, gently heated, and the UF6 flows as a clear vapor into the next process. Nothing dramatic to watch, just pipes and gauges, but this quiet change from powder to gas is the key that unlocks isotope separation. With UF6 in gaseous form, we're finally ready for the star of the show: high-speed centrifuges that enrich the uranium. Here's where the sorting marbles idea becomes real. Our uranium is now a gas, UF6, flowing through sealed stainless steel pipes into a hall full of tall, slim machines called centrifuges. Each one is basically a super precise, spinning cylinder inside a vacuum. When it spins, the slightly heavier UF6 molecules that contain U-238 feel a stronger outward push than the slightly lighter UF6 with U-235. That tiny mass difference, just over 1%, is all the centrifuge needs to start nudging the mix apart. Inside, the gas sets up a gentle internal circulation. Heavier molecules migrate a bit farther outward and downward. Lighter ones drift inward and upward. Small internal scoops collect those slightly different streams. No fireworks, no drama, just quiet separation driven by speed and balance. One centrifuge only makes a tiny improvement, so they're connected in long cascades. Hundreds or thousands of machines arranged in stages. The slightly enriched stream from one stage feeds the next, like stepping stones that raise the U-235 share from natural tilde 0.7% to the reactor target of about 3 to 5%. At the same time, another stream becomes depleted uranium, often called tails, which is stored for other uses such as shielding or left for potential re-enrichment later. Everything about this room is about control. The rotors spin at extreme speed, so the machines sit on isolation mounts inside vacuum housings to reduce friction and vibration. Operators watch screens tied to sensors that track temperature, pressure, and minute imbalances. If anything drifts out of spec, the system slows or stops a section automatically. The sound in a modern plant is a soft, steady hum, more like an air conditioner than a factory. You might hear the term SWU, separative work unit. Think of it as the effort needed to raise U-235 concentration. More enrichment, or starting with lower grade feed, means more SWUs. The point isn't the math. It's that centrifuges do the job with far less energy than older methods, which is why they dominate today. A clear boundary: reactor fuel enrichment tops out around 5%, U-235. That's very different from weapons grade levels around 90%, which require different goals, designs, and controls. Civil plants operate under strict national rules and international safeguards to ensure the product goes only to peaceful power reactors. Enrichment gives us UF6 gas with the right share of U-235, but you can't put gas in a reactor. First, the enriched UF6 is deconverted back into a solid, stable ceramic. In closed vessels, technicians warm the cylinder, draw out the gas, and run it through controlled chemical steps, think humidifying and filtering, to turn it into a fine black powder of uranium dioxide, UO2. UO2 is the industry's go-to fuel material because it stays strong at high temperatures and doesn't react much with water. Next comes pelletizing. Automated presses compact UO2 powder into small cylinders, pellets about 1 centimeter across. These green pellets are fragile, so they go into long furnaces for sintering. Hours at blistering heat fuse the grains together, shrink out pores, and raise density. The result is a hard, ceramic pellet that can take the heat and radiation inside a core without crumbling. Quality control here is obsessive. Laser gauges confirm each pellet's diameter and height within micrometers. X-ray checks catch hidden cracks or voids. Chemistry tests look for trace impurities that could absorb neutrons. Only pellets that pass everything move on. Robots then stack pellets into tubes made of zirconium alloy, silvery, corrosion-resistant metal that lets neutrons pass easily. Each tube becomes a fuel rod, sealed with precision welds and helium backfill to help conduct heat. Dozens of rods are then clamped into a rigid fuel assembly with a grid that keeps spacing perfect for coolant flow. Before shipping, assemblies face more tests. Ultrasound scans of welds, vibration checks to simulate reactor conditions, and scale readings to confirm the exact uranium load. Despite the energy locked inside, fresh fuel gives off very low radiation and can be handled with routine industrial precautions. A single assembly packs enough potential to power about 100 homes for a year, and the next stop is where that promise is unlocked: the reactor. Fuel assemblies slide into the core, grids of zirconium-clad rods packed with UO2 pellets. Inside each pellet, a small share of atoms are U-235. When a slow neutron strikes one, the nucleus splits, releasing heat plus more neutrons. Those new neutrons hit other U-235 atoms and the process repeats, a controlled chain reaction. Ordinary water does double duty. As a moderator, it slows fast neutrons, so they're more likely to cause fission. As a coolant, it carries heat away from the fuel. Control rods, made from neutron-hungry materials like boron or hafnium, act like the brakes. Inserted deeper, they soak up more neutrons and power drops. Withdrawn, power rises. Sensors watch temperature, pressure, and neutron flux constantly. If anything drifts out of bounds, the system inserts the rods in a heartbeat, and the reactor shuts down automatically. That heat makes steam. In pressurized water reactors, a closed primary loop carries hot water through a heat exchanger called a steam generator, where a separate water circuit boils into high-pressure steam. In boiling water reactors, the core's water boils directly. Either way, steam rushes to a turbine that spins at about 1,800 revolutions per minute, turning a generator that outputs hundreds of megawatts. Steady electricity for hundreds of thousands of homes. Afterward, the steam is condensed back to water and recycled, a quiet loop that runs for months between refueling outages. Surrounding it all is heavy shielding and a thick, steel-reinforced containment building, part of the multiple layers that keep the heat and the radiation where it belongs. Enrichment for power reactors happens under layers of oversight. Facilities are licensed, fenced, and monitored. Cylinders and batches carry unique IDs that link to paperwork from mine to plant. The International Atomic Energy Agency checks that what goes in and what comes out match, using cameras, tamper-indicating seals, and on-site inspections. If a seal is broken or a figure is off, the alarm is obvious. There's also a bright red line. Reactor fuel is low enriched, about 3 to 5% U-235. Going higher triggers stricter rules, more scrutiny, and different equipment. Nations enforce export controls, so only approved operators receive material and parts. Safety runs alongside security. UF6 areas use dry air and leak detectors. Workers train for chemical hazards like hydrogen fluoride. Physical protection plans cover guards, access control, and cybersecurity for control systems. It's not cloak and dagger. It's careful accounting and engineering discipline designed to make sure enriched uranium stays where it belongs. Fueling power plants. After about a year in the core, fuel assemblies are spent. They've given up most usable energy but remain intensely hot and radioactive. Robotic arms lift them into deep, crystal-clear cooling pools, around 8 meters of ultra-pure water that both cools and shields. You may notice a soft blue glow, Cherenkov radiation, a harmless light from fast particles moving through water. Over roughly a decade, heat and radioactivity drop. Many assemblies are then moved to dry cask storage, rugged steel and concrete cylinders with passive airflow. No pumps, no fans, just physics and thick shielding. Casks are sealed, monitored, and sited on protected pads designed to withstand extreme weather and earthquakes. For the very long term, countries plan deep geological repositories, stable rock hundreds of meters underground that can isolate waste for millennia. Some projects are already built or close to it. Through each stage, the theme stays the same. Multiple barriers, measured steps, and lots of monitoring. On today's supply, Kazakhstan leads with in-situ recovery. Canada and Australia follow. Conversion and enrichment capacity clusters in Europe, North America, and Russia, with new lines emerging to fuel next-generation reactors. From yellowcake to pellets to power, enrichment turns a rare isotope into steady electricity, safely engineered, tightly tracked, and ready for tomorrow. If you'd like to hear more untold stories behind the world's most critical systems, don't forget to subscribe.